balancing equations, but balancing equations using a particular method. And the method that we're going to be covering today is known as the oxidation number method. Let's have a look. So it must be noted that reactions must be balanced by mass and by charge. Now, like I said, we went through one method that we're going to be covering throughout today in this video, but there is a second one. Okay, so what we are dealing with today, like I said, was the oxidation number method, and in the next video we'll be looking at the second method, which is a little bit more complex and difficult. It's known as the half reaction. Okay, reactions, this stands for reaction. So the steps that we do right now, it's going to be a little bit limited because we're not going all the way for the half reaction method. We're stopping where we can just simply use the oxidation number method. So we'll continue this checklist later on in the next video, but for now, just follow along. Number one, we need to assign the oxidation number for each atom and identify Leo the lion says GR, right? So obviously L stands for losing, E stands for electrons, O stands for oxidation. Okay, so we need to identify the losing electrons of oxidation atoms that are part of the equation, and GR. Obviously this stands for reduction, and this is gaining electrons, all right? So we got to do this for both. And you should obviously be comfortable finding oxidation numbers for every single atom. If not, look at the previous videos for the oxidation number in case you're still confused. All right, number two, then you got to determine. You got to determine the number of electrons lost and gained. Then cancel out the number of electrons lost, and it must be equal the number of electrons gained. By using the simplest whole number. And then we use this whole number that you've deduced up here in step number 2, okay? And we're going to use it as the coefficient for the reactants and products containing oxidized and reduced species. To ensure the electrons that are transferred are balanced. And step number 4, last one, you balance anything that is remaining left over that needs to be balanced by site. Number 1, assign the oxidation number for each atom. So obviously this here is a 3, and we know that oxygen typically has a -2 charge. Obviously that's going to be -6. In total, the whole thing needs to equal 0 because there's no particular charge of the whole compound. And then hydrogen obviously typically has an ideal charge of 1, okay? So 1 plus what minus 6 will give you the 0, obviously 5. So we're going to be putting a 5 over there. Then we do the same thing over here. The whole thing has to equal 0. This was typically a negative 2, so 3 times negative 2 gives you a negative 6. This here typically has a charge of 1, right? So 1 times 3 gives you 3. So 3 plus what minus 6 will equal 0. Obviously this one here has to be 3. As we keep going along, this one also has a charge of 0, okay? Typically has a charge of negative 2 for the oxygen, so we have 1 oxygen, so 1 times negative 2 gives you negative 2. What does this number have to be? Minus 2 to equal 0, obviously a 2. So this one has to be a 2. This one over here, whole thing needs to equal 0. Again, oxygen is typically a negative 2, so 4 times negative 2 gives you negative 8. Hydrogen is typically a 1, so 3 times 1 gives you 3, so we have that there. So 3 plus what minus 8 will give you 0. Obviously this has to be a 5, so we'll be putting a 5 there. And this last one has to equal 0, so this is 1. This typically has a charge of negative 2, so 1 times negative 2 gives you negative 2. This is typically a charge of 1, so 1 times 2, right? So 1 times 2 gives you 2, so 2 minus 2 gives you 0. That checks out, so 1 and negative 2 are good. Now let's look at any discrepancy. So obviously the hydrogens have always been 1s, the oxygens have always been negative 2s. So where the discrepancy lies is the nitrogen and the arsenic. Okay, so we have this nitrogen over here. All right, it was at a 5, now it's down at a 2, so it's a reduction, it got reduced. Okay, that means it gained how many? It gained 3 electrons, because the difference between the 5 and the 2 is 3. Okay, so it's gotten a little bit more negative. That's what we're saying, it gained 3 electrons, because obviously electrons are negatively charged. Okay, so it used to be a 5, now it's at a 2, so it's a little bit more negative now. Then the other discrepancy was the arsenic. Okay, so we have 3 and then 5, so obviously this is oxidation. The oxidation number went up. That means we lost, what's the discrepancy? 3 and 5, obviously a 2, so we lost 2 electrons. Okay, so we just pretty much did step number 2, right? Determine the number of electrons lost and then gained, okay? So now we got to cancel out for these electrons lost to equal the amount of electrons gained by using its simplest whole number, okay? So what does this mean? This means we have to find a number that both of these can become, right? So obviously the simplest whole number between 3 and 2 would have to be a 6, right? Because 3 times 2 will give you 6 and 2 times 3 will give you 6. So if we were to write this out, I'm just going to rewrite all of this, okay? And then we're going to start plugging in where we need to plug it in. And let's put in our coefficients now, okay? So this thing over here, okay, and this thing over here, right? Both of those got gained by 3, so we need to make them equal the simplest whole number of 6, okay? So we're going to multiply these by 2 in order to give us 6, all right? So this one has to be multiplied by 2, and this has to be multiplied by 2. Now, this one over here and this one over here, these were lost, right? They were lost of 2 electrons. So in order to make the product of 6, they have to multiply by 3, okay? So now this becomes a 3, and now this becomes a 3. Now let's do our little chart for the elements. That's what the E represents. L stands for the left side and R stands for the right side. All right, so let's make sure these are balanced. Okay, so for my left side, for my nitrogen, how many do we have? We have 2. How about my right side? Okay, I also have 2. How about my arsenic on the left side? Okay, we have 3 arsenics. And how about on the right side over here? There are also 3 arsenics. For the left side over here, okay, we got 3 times 2 gives you the 6. And then of course this one is 3 times 3. That obviously gives us 9. So 9 plus 6 will give us 15. How about on this side over here for oxygens? We have 2 oxygens over here. And then we have 1 oxygen over here. So that will be 3. And then plus this one over here is 12 oxygens. So 12 plus 3 will give you 15. And then last one for the hydrogens over here, we have 2 hydrogens. And how about here? We have 3 times 3, 9. So 9 plus 2 gives you 11 hydrogens. And then how about on this side over here? We have 3 times 3 gives you 9 plus 2 hydrogens gives you 11. So it seems like we are all good. We've pretty much done number 3 here, right? We use that whole number as a coefficient. And then we try to ensure all the electrons that were transferred are balanced, and it seems like we've actually done that. Okay, so we could actually just omit step number 4. Okay, step number 4 is saying balance any remaining by site. Okay, so if this was not particularly balanced, we may have had to just eyeball or continue to use this chart and balance it on our own. In this case, we don't need to do that. We're all balanced, so we are good. So this is the answer. So we have Kim and a 4. Again, we always have to assign our oxidation numbers, all right? So this is all going to be equal to 0. So 4 times -2, right? Because oxygen tends to be a -2 charge, gives you -8. This is typically a 1, so we'll just put that over there. So 1 plus what? -8 is going to give you 0, obviously a 7. So this becomes a 7. Next, this one here also have to equal 0, so this typically a -2, so 2 times -2 gives you -4. This typically is a 1, so 1 plus what? -4 is going to equal 0, obviously a 3. So I'm going to be putting a 3 over there. This one over here, of course, it has to equal 0, so 4 times -2 is supposed to be -8. So this is typically a 1, right? So 2 times 1 gives you 2. 2 plus what? -8 is going to give you 0, obviously a 6, so that has to be a 6. This here whole thing needs to equal 0, typically a -2 charge, so 4 times -2 gives you -8. And then now this is where it gets a little bit tricky, right? Which one should we start with first, the Mn or the S? Well, so far we've already established that S is going to be a 6 on this one over here. So we can just establish that S here will also have to be a 6. All right, so that leaves our Mn, the one as a mystery. So 6 minus 8 will give you -2. So obviously what does this number have to be so that it equals 0 as a sum? Obviously a 2. So this becomes a 2. H2O over here, this has to equal 0. So again, typically a -2. So 1 times -2 gives you the -2. So this is already a charge of 1, right? So 2 times 1 gives you 2. That's perfect. So we're just going to leave these as such. This one here equals 0, so this has to be in charge of -2, so 3 times -2 gives you the -6. This is typically a charge of 1, so 1 plus what? -6 will give you 0, obviously a 5, so this is here is a 5. And this last one here has to equal 0, so 4 times -2 is supposed to give you -8. This is typically a charge of 1, so 2 times 1, right, gives you 2, right? So 2 plus what? -8 equals 0, obviously a 6, so this has to be a 6. Now that we've done that, let's look at a discrepancy. So obviously our sulfurs, right, were no discrepancy. There was no change. All the sulfurs seem to be a 6. And obviously our alkali metals, right, like potassium were no problem, right? Same with our H's. I mean, technically H is not a metal, right, but it is in group 1, and they've all had a charge of 1. So none of those have really changed. So what things have changed? Obviously the Mn, the manganese, and obviously the nitrogen. Okay, so this Mn, where is it? It's right over here, the next one. Okay, so again, 7 to 2, so it got reduced. Discrepancy is of a 5, right? So it gained 5 electrons, but a little bit more negative. And then for our nitrogen here, let's bring it. Where's my last nitrogen? Right over there. Okay, so it was at a 3, now it's at a 5, so it got oxidized. It gained oxidation number. So that means it lost. What's the difference between the 3 and the 5? Obviously a 2. So obviously just lost 2 electrons. So I'm just going to write this again here on the side. Alright, so that means this one over here, if it is at a 5, we got to find the simplest whole number, okay, so that we can cancel out the number of electrons lost to equal the number of electrons gained. Okay, so if this is 5 and this is 2, obviously this can become a 10. This could also become a 10, right? So 5 times 2 will give you the 10, 2 times 5 will give you the 10. So this one, right, this one over here, this one over here, they have to be multiplied by 2. And then for this one over here and for this one over here, they're at a 2, right? We've got to multiply by 5 to give us that 10. So let's multiply by 5, okay? So 5 over here and 5 over here. All right, so now we've got to check the left side and we've got to check the right side. All right, so our left side here, we can see that we have the potassiums. There are 2 of them. Oh, sorry, no, there's another 5 over there. So 5 plus 2 will give us 7. And then over here, we have 5 potassiums, another here. 2, so that adds up to 7, so we got 7 and 7. So our Mn, that's this one over here, we only have 2 Mn's, and on the right side also just 2 Mn's. For our nitrogen we have just 5 N's, and on this side over here we have also just 5 N's. For our sulfur, where is our sulfur? We have 1 over here. And for our right side, we have 1, and we have 2 and 3. And then for oxygens, we have 4 times 2, which is obviously just going to give us 8. This one here, 5 times 2 gives us 10, so 10 plus 8 will give you 18, plus 4 over here will give us 22. On our right side over here for oxygen, so this one over here, there is 8 oxygens. We got 1 over here, so that's 1 oxygen there, and then this one here, 5 times 3 gives you 15 oxygens, and you add another 4, so that should give us about 28. And our hydrogens here on the left side, we have 2 hydrogens, and the hydrogens here, we got 2 as well. So as you can see, unlike the previous example, this is not as clear cut. We thought we would be able to end on number 3, but we cannot. We are still unbalanced, so we gotta now balance anything remaining by site. Okay, so obviously these non-metals here are good. We just gotta deal with this non-metal over here with the sulfur. Okay, so again, we have 3 sulfurs on this side. We only have 1 over here, so it makes sense to be putting a 3 in front of this sulfuric acid. So then we just can make it for hydrogens over here, we got 3 times 2, so this becomes 6. And then for our sulfurs, this becomes a 3, nice. And then for our oxygens, 4 times 3 will give you 12, okay? So we now have 12 oxygens over here, all right? So if we have 12 oxygens over here, and we have 10 oxygens over here, and we have 8 oxygens over there, what do we get when we sum them all up? So obviously 10 plus 12 is give us 22, plus 8 will give you 30. So where can we continue doing this? On this side over here, where we just affect the oxygens and the hydrogens, all right? Because obviously these here, right, are all fine. We don't want to touch those. So obviously we have a nice, thankfully, a clean H2O there to do the job for us. So obviously this is kind of a, upsetting up there, right? It's a little bit complex. So let's just deal with the 2 and the 6, right? For the hydrogens, we typically go oxygen first and then the hydrogens after. But in this case, obviously it's a lot more sound to be using the hydrogen first, okay? So obviously we have 2 over there. We need to make 6. We'll just add a 3 over there. So 3 times 2 will give us that 6. And obviously that 3 is going to be 3 oxygens over here, okay? So now let's add up all the oxygens just to make sure that we actually end up getting 30, okay? So we have how many here? 4 times 2 will give us 8. How many over here? 5 times 3 will give us 15. And how many here? We have 4. So if you add them all up, getting 30. That is the answer. Right, balanced half reactions. Okay, so how the heck do we do a half reaction? Well, we're just going to establish what are the connections. Okay, so obviously Al is connected with this Al, and obviously this Fe is connected with that Fe. So let's just start with the Als first. I'm just going to write them out individually on their own. And this one here is also on its own. And how can we make sure that they are balanced in terms of the charge? Okay, well, this one has 3 electrons that have been lost. So as long as we add 3 more electrons, because obviously electrons are negative, now this plus 3 and this negative 3 cancel out to make equal 0. So now we are good over here. So we've done actually our first half reaction. Now we got to do our second half reaction. So we have Fe 3 plus. AQ is supposed to yield another Fe. This one here is a solid. So obviously this one here is a 3 plus. It's a little bit positive, so we're going to make it a little bit negative. So we'll put the electron stuck over there. So now we have 3 minus 3 will give you 0. So this here is our half reaction. So honestly, this is it. That's the answer. All right, let's try this one over here. Okay, write balanced half reactions for each of the following equations, okay? But it does say that we have to write net ionic equations first, okay? So we have our Sn, solid, and of course this can be broken up. So we're just going to change this Pb has a charge of obviously a 2, so we'll put that 2 plus up there. It is in aqueous. And then there is 2 chlorines that we know chlorine has a charge of -1, so we'll put that over there. Okay, so now let's yield it. Our Sn, again, we can see that it has a charge of 2, so we'll put a 2 plus up there. This is aqueous. And then we add it with our 2 chlorines. Again, we know that chlorine has a charge of -1, all right? So we're just going to add PbS. So, of course, where are our like terms that can cancel? This one and this one goes away. So we're just going to continue breaking this downwards. Now we have to do our half reactions, okay? We gotta balance these half reactions. So let's start with this SN. What is it yielding? SN2 plus. Of course, this one's slightly positive with the 2, so we gotta add slightly negative the electron, so now we are good, okay? Now it's completely neutral. We'll do the same thing for our PB. What is it yielding? Our PBS. Of course, slightly positive. Balance it out with a slightly negative 2 electrons. We are good. This is the answer. So these are the 3 green questions of the day. This is the first question, this is the second question, this is the third question. First, the first question over here, if you manage to do step 2 and step 3 correctly and you found out the smallest, simplest whole number coefficient, okay, that's not actually just a set fixed number. You could absolutely change it, okay? So as you're doing your step 4 to find out any discrepancies, if it hasn't balanced out naturally itself, you could absolutely change the coefficients in order to make sure that you can balance it out properly, okay? So don't be afraid to do that. All right, so please pause the video and I'll be giving you the answers shortly. Try these on your own. This is the answer to the first question. This is the answer to the second question. This is the answer to the third question.